Okay, so as noted, today we're going to talk about cyclic peptides, and then next class we're going to be moving into bioconjugation chemistry. And I want to talk about sort of what stabilizes peptides and how we can think about peptides, especially as drug materials or as biomaterials for other kinds of applications. So we finished last class talking about native chemical ligation, which is a way to connect different peptides together. I was thinking about discussing a few other methods. They're in the notes, but they really get into sort of heavy organic chemistry, and I decided that they don't add a lot of extra value. There are other, basically I can summarize it by saying there are alternatives to native chemical ligations. Cysteine-free alternatives. That use serine or threonine instead. So people have kind of found a way to use an oxygen nucleophile instead of a sulfur nucleophile to do essentially the same kind of thing. There are also lots of new additions and modifications to the native chemical ligation to make it a little bit more robust and a little bit more selective. Again, we can get in. We could spend weeks discussing it. I don't think there's a lot of a point. If you do come into doing that, and if you're ever involved in trying to figure out how to stick two peptides together, after this class, I said I'm going to drop in some papers on bioconjugation. I'll drop in a couple of good recent reviews that talk about more general approaches to peptide-peptide linkage using native chemical ligation and modifications and alternatives to native chemical ligation. But I think going into the details, I'd love to, but it really does mean wandering around the weeds a little bit on carbonyl chemistry, and I don't necessarily see that there's a lot of value to doing that. Okay, so what I want to talk about is peptide stabilization. So why is this a problem? Because so far we've been talking about linear peptides. You got a peptide, you got an N-terminus peptide, C-terminus. Like this is what peptides are like in your body. Problem being, generally not useful drugs. Any idea why those are pretty shitty drugs generally?
Not selective enough?
No, normally they're really, really selective. Most peptides are ridiculously selective.
That's what I'm thinking, but
so what does a drug need to be able to do? Let's think about what and just as a general concept. I think this is actually a valuable sort of sidebar on it on the course. I guess it's not really biomaterials or these things, but useful. What does a drug need to do?
Change something.
Change something. Okay, I'll accept that. Do you want to be a bit more specific? Like, if I want to change something, I can, flip a switch. I can petition my member of parliament. That's actually not going to change anything, is it? Lying. I can go knock something over or do something. But what does a drug? What can a drug do to change something?
And for example, block something or
Okay, I like the block something. Can we change the word something to something more specific?
Bind with proteins.
Yeah, okay, block a protein. I like that.
Well, actually, I'm thinking binding with, but yeah.
Bind protein. I think it is that it's not universally true. There are occasional drugs that bind DNA. There are occasional drugs that bind sugars or bind lipids, but those are in a vast minority. I'd say bind protein is probably greater than 98% of drugs. And the only reason I'm not saying greater than 99 is because I can be sure that that number is correct. There might be enough DNA binding drugs out there now that it's starting to crawl up to about 2% of the market. But drugs bind protein. It's kind of what they do. Okay, so your drug needs to bind protein. Sweet. Is that sufficient for a drug to be a drug?
Since you're asking, I would say no.
Sorry?
Since you're asking, I would say no.
Yeah. No, it's not sufficient. What else does a drug need to be able to do? And I'll give us for free specific to a subset of proteins. Often it's a single protein, but sometimes a subset's more useful. Yeah, I guess it's a corollary of that. Oh, that's the one I wanted. Bind in a way that affects the protein. Because you can bind to a protein without actually doing anything to the protein. In which case you have a binder, but it's not a drug. Could be a probe, maybe, but it's not a drug. Okay, so I would say that if your drug, if proteins were swimming around in water, just like in the ocean, and did their own thing, this would be sufficient for a drug to be a drug. But proteins aren't swimming around in the ocean.
No, and it's actually very problematic.
Sorry, what's problematic?
That's not sufficient, and it could be problematic.
Okay, so yeah, so what more do we need?
Swimming around. Wait, let me think about this.
Yeah. I think for the M&B students too, this is really, really relevant to what you're doing and how you're thinking about designing anything. So any of you
something
go on.
something specific. I mean, that drug can find its way. I mean, the drug has to have some specific things to find its location. I mean,
Has to be able to localize to its target. So that can mean penetrate cell membrane. It can mean you need to be soluble in blood, lymph, extracellular matrix.
or at least attached to something that things can do such a things for the drug.
Yep, or be transported by a carrier.
Or to avoid the first pass effect. It's
Yeah.
too
Okay.
specific.
Nope. That's good. No, I like that. So, but I'm going to actually add that as the third thing. This is where I'm kind of going. So 1, 2, 3 needs to survive. Okay. So it needs to avoid liver metabolism. So you can do that in two ways, right? You can either design a molecule that can be orally taken and that passes through the intestine into the liver, doesn't get destroyed by the liver, and then passes into the bloodstream. That's one option. Or you inject the drug directly into the bloodstream and you bypass the liver. Alternatives to injection are inhalation, because then you just absorb through the mucosal linings of your lung directly into the bloodstream. Or you can do it through transmucosal transfer inside the mouth, so it transfers to the mucosal membranes in the mouth, so you're not actually going into the intestine. Or you can do transdermal, where you transfer across the skin directly into the bloodstream. All those things get your drug directly into the bloodstream without going into the liver. So the liver is one thing. What else can destroy drugs outside the liver?
Digestion system.
Well, I'm going to say the digestion system is like, if we're talking like the human digestion system, I'm going to say that's part of the whole first pass metabolism, intestine, stomach, and all that stuff. But if you're in the bloodstream, you have all the enzymes in the blood. Because your body is constantly pumping out enzymes to degrade things that are outside of cells. And then what's the enzyme? I always get lysozyme and lysosome mixed up. And then we have the other problem is degradation of lysosomes of target cells. So, most drugs that work on surface receptors of cells are great because it doesn't need to get into the cell at all. It interacts with something on the surface. It's wonderful. But any drug that operates on something inside of the cell, so let's think of a particularly relevant example. If we're thinking about drugs that target, let's use this maybe as the example for the rest of the day. Drugs that target the main protease of SARS-CoV-2. So if you know how SARS-CoV-2 works, it gets into the cell. It's then a kind of a weird virus because it only makes, I believe, 3 different polypeptides in the cell. One is the main protease. The second one is, so I can't remember which one, is one of the DNA handling enzymes. And I think the third one is basically everything else, all as one really, really, really long polypeptide. And then the main protease cuts that in specific places to liberate all the individual proteins that the SARS-CoV-2 needs to replicate. It's very, very clever. It's a smart little bug. So the main protease cuts peptides, so it shouldn't be too surprising that a lot of drugs that target the main protease might look like peptides. because if its target is peptides, you might want the drug that targets it to be peptides, because if it's used to handling peptides, maybe peptides fit pretty well into it. So let's say we're targeting a main protease. The main protease is inside the cell. But the way your drug, you've injected this drug, it's circulating through the bloodstream, it passes by one of these cells. The way the cell gets inside the cell is through endocytosis, generally. So it just kind of like samples stuff from its environment, right, and brings it into a vesicle. And that's how a lot of cells gather nutrients from outside of themselves, things that can't pass through the membrane and don't have active transport. Now, that vesicle that I just created, it's not going to suddenly just release it. That's insane. That's dangerous. It takes it to these processing facilities and merges it with the lysosomes. And the lysosomes are these internal cellular compartments that are full of digestive enzymes. And they break shit up. That's what they do. They turn all that beautiful external stuff that you just grabbed into basic building blocks. Then that can get released to the cell, and the cell can then use those building blocks to make stuff. So your drug needs to do basically these three things to be a drug, right? Your drug needs to actually have action. It needs to target the protein you want to target. It needs to be able to get to that protein, and it needs to be able to survive long enough to get to that protein and do its thing, and survive long enough at the protein to do its thing. Because if you make a drug and it targets the protein really well, but as soon as it enters the cell, it breaks down, it's not a useful drug, right? Because it just broke down. It's not doing its thing. So these are the three requirements of any drug. You could add a fourth requirement, depending how you want to define requirement number one. Doesn't kill you. Or make you very sick. I'm going to put the second one in brackets because we do have lots of drugs that make you very sick that we're pretty happy with. All the chemotherapeutics make you very, very sick. But hopefully they don't kill you. So it's ideal if a drug doesn't kill you. Otherwise, it's not a very good drug. But we could sort of make number four as kind of a corollary of number one. We just need to bind the right things. So this is what every drug needs to do. Let's step back and think about peptides. Where do we have problems with peptides along this chain? So let's say we can get binding things, and that's no problem. And when we think about drugs, it's often, especially as academics, especially as people just starting out, we think about, oh, my drug needs to bind its target. Absolutely, yes, it absolutely does. You just can't lose track of the other three things. And it's so easy for people to forget about them and not think about them when they're designing stuff. So peptides have an absolutely major flaw in one of these.
Degradation.
Sorry?
I mean, we should try to do something that they do not degrade.
Right. So what do you think about how easy peptides degrade?
Because of the two N that they have, and terminus and C terminus that they have, and they can easily react with other things that we have in the body.
Peptides degrade really, really fast. Peptide lifetimes can be incredibly short. You've got two classes of proteins that we need to worry about with these. We have the endopeptidases. So these are peptide enzymes that cleave peptides within the peptide or proteins within the protein, and they cleave very specific sequences. Maybe like an alanine, phenylalanine, alanine unit, and they'll cleave between the first alanine and the phenylalanine, but they need to see all three to fit into the binding pocket. Normally, these are associated with processing things, but they're also quite a few of them in the lysosome, and they're kind of they have a lot of variety, and they kind of chew up proteins in the middle. For peptides, though, we need to worry more about exopeptidases. Normally, these are identity independent. They don't care what the peptide is. And they kind of chew on the peptide from N terminus or C terminus. There are N-terminal exopeptidases and there are C-terminal exopeptidases. And either way, we chew away from one way or the other. So you take your drug, you spend a lot of money, a lot of effort to make this damn thing. You inject it into somebody, and some stupid exopeptidase starts chewing away on your drug when it's in the bloodstream, and your drug never actually gets it to the site of action, and everything kind of fails.
So is that where the names come from? Endo and Exo.
Yeah.
So endo
Endo
kind
is
of-
inside, exo is outside.
Yep, that makes perfect sense.
Yeah, so I can actually make a note of that. Or internal, I guess. But I'm a Northern European, so I'm always thinking in terms of the great outdoors. As our barbaric Northern European ancestors always use these terms. So, but you can use internal and external as well, I guess, or outer and inner. Whatever makes sense to you. So these are the enemy of peptide drugs, because you got this peptide drug, it's only 13 amino acids long. If you start chewing away at that, you're going to lose activity really fast. Compared to if you have a massive protein, it takes an exopeptidase a little bit longer to chew through like a 300 amino acid protein and for it to lose all of its activity. Okay, that's a problem. Now, endopeptidases aren't normally as big an issue for peptides because, again, they cleave specific sequences. The chance that you have that specific sequence in your peptide is pretty low. So you're normally pretty safe for most endopeptidases. It's the exopeptidases that get you. So I want to talk about four stabilization strategies, really. And if you're curious about this, we actually have exactly the same issue with RNA and DNA. There's endonucleases, and you can think of these as the restriction enzymes that we use to edit plasmids and things. Like they cut a specific DNA sequence. And then there's exonucleases, which just chew away RNA or DNA from the outside in. And RNases are mostly the exo ones, and they're just ubiquitous. They're absolutely everywhere in the environment, and that's why you need to be really careful when you buy glassware or plasticware that you're going to do anything with RNA or DNA, and it often says RNA is free. They do a special processing to remove all protein, because if there is any protein present, it's probably in RNAs, or it's at glycosidase. Either way, it's bad for nucleic acids. So these aren't amino acid specific things. These are problems with linear biomolecules. Sugars avoid a lot of these because they're kind of complex, but that's why you have this huge, rich environment of glycosidases all through your body that cleave the sugars. Mostly we make stuff to destroy it, right? We make proteins, peptides, sugars, nucleic acids, whatever, lipids. our cells make it, they use it for a bit, they destroy it. So we have a really, really rich machinery of ways to destroy things, especially anything that's foreign. And any drug, by definition, is foreign to the cell. Okay, so the 4 stabilization strategies I want to talk about. Well, let's think about it. Let's see if we can actually come up with the some of the 4. We're not going to come up with all of them because a couple of them are a little bit repetitive. But what do you think about ways that we can disrupt exo or endopeptidases?
I've been thinking because I think that's actually the DNA does, like it has some extra sequence. Because yeah.
So DNA has like extra stuff on the end, you mean?
Yeah, I think so. Basically, when you replicate, like when our bodies replicated, like at some point it start losing the very end of the sequence, and which is why there's always some extra, just like there from the beginning.
Yeah, you have the telomeres, right, on your chromosomes. And we have telomerase, which can add more telomere to the end, which is just extra material. Our chromosomes are all packed up pretty tightly, so they're pretty well protected. So on the RNA, they're available. Adding extra residues to the end probably would slow it, but it's not actually very viable because one of the problems with adding extra residues is that you can really change the shape of your protein. So or peptide. So you don't see. I agree. I hadn't actually thought about that, but adding extra residues would extend the lifetime. I don't know if it would meaningfully extend it because once an exopeptase is kind of grabbed on, it doesn't let go. It just chews through them. So it would chew through the extra ones and then start chewing up your peptide. But I think it could slow it down a bit, and there would always be some diffusion away from the enzyme. So I'm gonna change it. I'm gonna give you that one, Hazel. I think that's a good idea. I hadn't thought about that.
It's a tricky one.
Add extra buffer residues. Okay. Let's think about other ways though we can stabilize them. Because remember, what we want is we want the peptide to have shape, right? Or structure, or the interactions. So we want specific interactions to be present in the peptide. We want it to have the right shape. Other than that, we have a lot of flexibility with what we do. So the first one I'm going to put down here is just cyclize the peptide. If peptide has no ends, because it's a circle, no exopeptidase sensitivity. So if you don't have a C terminus or an N terminus because your C terminus is tied to your N terminus, then exopeptidases don't have anything to grab onto. It is cool, isn't it? What else can we do?
I'm not thinking of anything because.
Okay, well then we'll run through the main ones. So one is we can use unnatural amino acids because a peptidase needs to bind to especially bulky ones, slow peptidase activity. And that's because a peptidase needs to be able to bind to the peptide. And so it fits specific or most natural amino acids. But if you introduce unnatural amino acids, suddenly they can't fit into the binding site and the peptidase can't bind.
This is a way of protecting.
Yeah, so we're trying to improve survivability. A second way is N-methylation. Actually, I'm going to just change it to N-alkylation. And we're going to see two different versions of this. This removes the NH amide bond. Well, it's not the amide bond, it removes the NH in the amide bond. And knowing how peptides and proteins bind other peptides and proteins, a lot of it is driven by hydrogen bonding interactions. And so a lot of them go, okay, well, I know there's always going to be an NH bond because every peptide has an NH bond, except for proline. Proline's weird. But, everything else, if you have a linear sequence, there's an amide, and it's a primary amide. It's NH bound to a carbonyl. So I expect to see the NH. And when an NH is gone, suddenly you don't bind to the peptidase anymore because it's looking for the NH and there isn't an NH. So removing the NH can slow activity. And the final one is change the backbone. I'm going to take a look at a couple ways to do this. And what you can essentially do is shift the reading frame. So what do I mean by that? Well, a peptide is NH alpha carbon carbonyl carbon, NH alpha carbon carbonyl carbon, NH alpha carbon carbonyl carbon. So if you're expecting a sequence, you space yourself a certain way so that you know, okay, so I'm going to bind the NH over here from this amino acid. I'm going to bind the carbonyl from this next amino acid, and I'm going to be set up to cleave the peptide bond on the next amino acid. If I suddenly change distances in there, suddenly the enzyme isn't set up to cleave the carbonyl bond on the next amino acid because it's not there. It's over an atom or two. And suddenly I've confused the hell out of the enzymes because stuff isn't where they expect it to be. And so the enzyme needs to bind, and that sets up this really specific binding interaction catalyst site where it does its scissoring. But if I've got my cell phone here and I've got a knife and I'm used to cutting a cell phone at this point, but suddenly I change where the cell phone is and my binding site gets shuffled over a bit and my knife is cutting here, then there's no cell phone there. And there's nothing to cut. So if I can change where I grip this, or I change the size of my cell phone, going from this bigger cell phone to the smaller cell phone, which no longer works because I lost it underneath the couch and I misplaced it for about 1.5 years. So I bought a new cell phone, and then I found it a few weeks ago, and it's got pictures from all sorts of these important parts of my life. But anyways, I found my old cell phone. But if I'm used to handling cell phones this size and I have a cell phone this size, suddenly all my machinery that is used to this kind of cell phone isn't going to work on this one because the sizes are different, because I fucked with the sizing. So if we can fuck with the sizing, we can screw up how proteins can interact with peptides. So essentially we've got 5 ways here. We cyclize, we remove the ends. We use unnatural amino acids which bulk it up so it no longer fits into the protein. We use N-alkylation so that it no longer recognizes NH bonds, which then hurts its ability to bind this thing. They're kind of associated. Or we shift reading frames. We shift the physical spacing of things by changing the backbone. Or we can use, as Hadriel pointed out, and I don't see any reason why not, we can use extra buffer residues. Now, these are not mutually exclusive. You can combine these together to make more stable peptides. And I would say that this lecture thing here is probably the last 15 years or so we've really been thinking about this. Because before about 15 years ago, there weren't a lot of peptide drugs because everyone was trying to make peptides, and the peptide drug par excellence that's really dominated everything is insulin, right? We make metric tons of insulin, like literally tons, kilotons of insulin around the world for diabetes. And it's just the normal insulin peptide. And we inject a lot of it and it does its thing. And insulin is kind of resistant to peptidases and it gets to the places you want and you put a lot of it in you. But a lot of other peptide drugs were failing. There was a lot of small molecule stuff that could be done. It was easy, so we did that. And it's only been the last, 15, 20 years that we've really turned our attention to the idea of, oh shit, maybe we should consider using peptides as drugs, and then we have to solve these challenges, and these are some of the solutions that have come up. Okay. So let's think about some of these. So I'm going to actually start with an alkylation. Mostly because it's the easiest. So there's two different types of alkylated peptides. There's the simple ones, the N-methylated ones. So you take a standard alpha amino acid. Let's say your favorite alpha amino acid is, I don't know, phenylalanine. Good amino acid. You methylate it. Normally the methylation conditions for this would be formaldehyde, sodium cyanoborohydride, sodium cyanoboro, and this goes through imine, to give you the N-methyl. Just a comment here for those not as familiar with stereochemistry. The wedge, of course, means is coming out of the plane towards me, but note that that's true when this relationship here is the nitrogens to the left and down. When I flip it like this, what I've done is I've taken a molecule and I've flipped it upside down. So now that that benzyl group of phenylalanine needs to be pointing into the plane and away from me. It's just 3D, right? It's just how that works. If I flip something upside down, it's upside down. So what I've just done is I've methylated this thing. Then I can do my standard, solid phase peptide synthesis. I can stick an FMOC on there. FMOC chloride. And nothing is stopping me just throwing it onto my peptide synthesizer and incorporating it like a normal amino acid. Except now I don't have that hydrogen on the amide, right? I'm going to have a CH3 group. So that's going to mess up peptidases. That increases the stability of the peptidases. The cost I'm paying for this, though, is I've removed the NH group. So if that hydrogen bond of that amide is important for the peptide doing its thing, that was a very bad idea. But you need to know if that NH bond is important or not. And the NH bond might be important for the peptide adopting a secondary structure which allows it to get to and localize to the right protein. It might be important for how it directly binds the protein. It might be important for how the peptide interacts with the receptor that gets it to the protein. So we have to be very cautious removing NH groups. But it's really, really powerful when it works because suddenly you've confused the hell out of a peptidase. So if we're using these more as materials and less for bio purposes, there's some stuff called peptoids. And the idea behind a peptoid is that Amino acids are hard. Let's make them easier. So it's kind of taking this strategy into a conclusion. So instead of, you know, this, which is an amino acid, we have a peptide amino acid. Note that the difference being is that I'm going to get rid of all the NHs. And I'm also going to get rid of anything at the alpha carbon. Normally you have the side chain on there. Now I have the side chain on nitrogen. These are really easy to make, of course, because all I do is I take glycine, I treat it as above with any aldehyde, and then I can do FMOC chemistry and connect these things together. To the best of my knowledge, there are no peptide drugs yet. I think that's more a matter of time, with this as being a relatively recent technology. But I also think a limitation is a pure peptide drug has no NH bonds, and the NH bonds tend to be pretty important for how peptides interact with their targets. And so I'm not going to be overly surprised if we never see a peptide drug, but peptoids, because of this ease of synthesis and because you can use peptide chemistry to make the polymers, make really, really, really good structural materials. And so we're starting to see peptoids being used to make new types of nanoparticles, new types of surfaces for electrical materials like photovoltaic cells and batteries. And people are looking into this because we can customize what the R group is to create any kind of function we want. And we have a very easy way to polymerize these kinds of things because we really know how to make peptides pretty well. So suddenly we have access to all these new types of materials. But they're not normally very good drugs, again, or no, as far as I know, none of them have been used as drugs, again, because you remove the NH bond. However, nothing is forcing you to make a peptide entirely out of peptoid amino acids. You can make a peptide by mixing and matching peptoid amino acids and normal amino acids. And I think we're going to see a lot of really interesting drugs coming out of that. You start thinking about the amount of chemical space you can cover, the number of options, the number of different things you can make, and your mind starts spinning because it's essentially infinite. And there's got to be something good in there, right? Like infinity is a big number. There's got to be useful stuff in infinities. So the next thing I want to talk about is shifting the frame. So there's two subclasses I want to talk about here. The first one is beta amino acids. So again, this is the alpha carbon because it is alpha to the acid carbon. A beta amino acid has the R group and a nitrogen by default, beta to the carboxylic acid. So what we've just done, right, is we've added an extra CH2 between the amine and the carboxylic acid. So we suddenly change the spacing there. That can have humongous effects, not only on peptidases, but also on drugs, anything else, because suddenly everything is a little bit further apart, and it's going to change how things fold. Integrating a single beta amino acid into a complex protein can completely change the folding pattern of the entire protein. So if you're trying to make a functional protein, that's probably not a good idea. But if you're trying to screw up a functional protein with a drug, it could be an amazing idea, because suddenly you can access a different shape with your peptide. So I kind of like the way these are made, so we're going to discuss it, because you make them again from the alpha amino acid. What you do is you activate the alpha amino acid. The typical way of doing it for no reason that I really understand is to use this reagent, isobutyl chloroformate, mixed anhydride, and what happens basically is that plus CO2 and chlorine. Okay, I don't quite understand where this is getting us. That's fair. Then this gets treated with diazomethane. I'm not quite sure why we use isobutyl chloroformate. We just do. If you look up protocols for this, they all use it. I've used it. It works great. I think it's more of a if it ain't broke, don't fix it kind of strategy, rather than a this is the absolute best way to do this in the entire world. So we have this molecule. This then deprotonates. Give us a nice stable zwitterion. And whenever you have, right after deprotonation, anytime you have something that can make nitrogen gas like this, it makes nitrogen gas. So we saw diazomethane methylating amino acids. We're not quite doing that here because we didn't use diazomethane as the electrophile. We use it as the nucleophile. And so what do we get if we draw that arrow I just drew? Well, it has a lone pair and a negative charge. It's also got a positive charge. It's called a carbene. It's not stable because it's both positive and negative. If you think in terms of orbitals, you have an empty p orbital, which is the positive charge, and you have a filled sp3 orbital, or sp2 orbital, sorry, which has 2 electrons in it, is a negative charge. So it acts as both a plus and a minus charge. And what does that do? Change the color for the arrow here. Just going to draw a single arrow to demonstrate the intermediate, because this is a what the hell just happened here moment. So we made a new bond to the carbon. The carbon is still attached to the carbon with the oxygen, but now if I follow the methods through, this is negatively charged, that is positively charged, because this carbon here lost 2 electrons that were in a bond that just migrated, and the other carbon just gained 2. So that's obviously silly. So let's just make a bond. And there's no hydrogen on that final carbon. It just is a carbonyl like that. A dot means carbon, by the way. I don't know why we do that. It's the convention. It is how this is drawn. You don't draw a C there, you write dot. Sorry, there is a hydrogen still on here. Let's keep track of that. Okay, at this point, it's unsurprising that you might be treating this with water. If we follow that through, and then it's a pretty quick and easy proton transfer. I draw it as reversible. It is not, of course, reversible. So a hydrogen comes in from water, a hydrogen is lost to water. I'm just not going to draw all those arrows out because, frankly, they're boring. But we're just going to clean up our charges. So now I'm actually just going to so we're going to lose the hydrogen that's on the water. We're going to gain another hydrogen on this carbon. Now it's neutral. It's a CH2. And we have generated the acid. So what we've done here is we switched, like it's a lot of arrows. It looks hard, but it's really, really easy. You do this in about 10 minutes in the lab once you make your diazomethane. And so you really easily convert your, we need a bit of heat here. You really easily convert your alpha amino acid into a beta amino acid. And note that at no point do you ever mess with the stereochemistry of this R group. So you can make use of all your natural alpha amino acids. You don't need to make anything. You don't need to worry about stereochemistry. You just make beta amino acids from alpha amino acids. And I think that's really cool, because now beta amino acids screw up the reading frame of peptidases, and they get very, very confused with them. And they cleave beta amino acids like orders of magnitude slower than alpha amino acids. The other thing we can do to mess this up is, and we're going to talk a lot about this next week when we start talking about bioconjugation, is the idea of isostears. So an isostear is isosteric, so something with the same shape. So one that gets used a lot for the peptide bond maybe withdrawing bonding goes quite right. Is this? This is the triazole. And one of the arguments is that, well, look, this distance, sorry, I didn't change color. The distance is the same between the R groups. These are H bond donors. That's a carbon hydrogen bond, so we don't think of it as an H bond donor, but that carbon hydrogen bond is so acidic that you actually sometimes see it exchange over NMR timeframes, and you don't actually see a CH there because it's like an NH, it's just switching with the solvent very quickly. Dipoles are about the same. The directionality and the magnitude of the dipole is about the same, and both are pretty rigid. Amide bonds don't really rotate because there's kind of a quasi-double bond between nitrogen and carbon due to resonance. And the triazole, of course, doesn't rotate because it's a freaking triazole. And I missed a double bond in the triazole there. It must be there. So there was a lot of fuss made that the triazole and the amide bond were the same thing. They're not. They're clearly not the same thing. But the hype wasn't all hype in that you can replace some amides with triazoles. And of course, an enzyme that is designed to break up an amide bond takes one look at a triazole and goes, what the fuck do you want me to do with this? Right? Like the enzyme is trying to use water to cleave a carbon-nitrogen bond to generate a carboxylic acid and an amine back. That's how peptidases work. It takes a look at a triazole. There are no carbonyls in there. There's nothing for it to cleave. It can't cleave the bond. Enzymes can't do anything with the triazole. So triazoles cannot be cleaved by enzymes. You can't. There's nothing to do. So again, in this case, we're not shifting the reading frame, we're changing the background bone. We are not going to finish cyclic peptides today. That's okay. So, the next thing is just unnatural amino acids. I don't really have a lot to say on this. Like I have a million things to say, but it's how much of it's relevant for this intro course. Not much of it. So basically, natural amino acids R equals 1 of 20 things. I'm going to say about 20 because there are 20 canonical amino acids in mammalian. things, but then we have a few other ones which people would argue, it's not all that unnatural. You know, the enzymes are designed to cleave things like ornithine or citrulline or homocysteine or selenomethionine. You know, there's another 10 or so amino acids which are pretty freaking common. But you start messing with the R group substantially, you make something like, I don't know, like an enzyme has absolutely no idea what to do with that, right? That's bulkier than any natural amino acid. You've got tons of aromatic groups. They're going to take up a lot of space. They're going to force into things. Your amino acid, your peptides are trying to cleave your amino acid. You're going to have a really hard time getting close to either the carboxylic acid or the nitrogen because there's this big thing in a way. And there's no enzyme, there's no evolutionary design enzyme that can overcome that. So if you can use unnatural amino acids, you can just screw up peptidases because they have no idea what to do. The other benefit of the unnatural amino acids is you can add function to peptides and proteins that doesn't exist. Like, for example, I've drawn here, this is going to be ridiculously fluorescent. That could be useful to have a really fluorescent peptide. So your peptide just glows and you can sort of visualize and image it when it's going through cells or going through organisms or whatever you're looking at. You can also add other functional groups, like you can do chemistry with proteins or DNA or whatever, or interact covalently and bind to stuff, or so that you can get intramolecular interactions because you have really, really strong hydrogen bond donors or really, really strong hydrogen bond acceptors that don't exist in nature. They're going to do it a whole lot better than natural ones. Right now, there's almost a fetish around adding fluorines to things. Fluorine is really electron withdrawing. It really strengthens hydrogen bond donation from adjacent alcohols and acids and amines and stuff. And so you can make a lot stronger bonds by sticking in fluorines onto molecules. Like, it's definitely useful, but I think we're going to run into some you have to be careful because I think of toxicity of alkyl fluorines, and we don't really understand what they do in the body because you don't have there's not a lot of fluorine in you. It's not bonded to carbon. Like, there are no sugars or peptides or amino acids that have fluorine bound to them naturally in our body. So we have a difficulty processing fluorinated molecules. And I think the final one that we want to really spend probably some time on, is going to spill over to next class, is cyclization. So there's a bunch of ways we can cyclize a peptide. So let's say we have a standard peptide. I'm going to just peptide, this is this block, this thing in the middle. We can do what's called a head-to-tail cyclization. And that's when you take you just basically attach those two together. So your head and your tail cyclizes. So your entire peptide is one circle. But not all peptides are like that. Often you'll have a peptide where you might have maybe an aspartic acid residue, maybe a lysine residue, and then let's draw those in. Well, aspartic acid, I'm going to redraw this a little bit. Watch me fuck up aspartic acid. I'm actually going to look it up because I always get my aspartic acid and glutamic acid separate or confused. And that is why This is an open book course. It doesn't get easier, I think, to actually keep track of all these. Okay, aspartic acid is only 1 carbon. Let's say we have our lysine. Lots of other residues in here. 1, 2, 3, 4. So we have an N terminus, we have a C terminus, we have an internal nitrogen, amine, we have an internal acid. There's nothing stopping us doing different types of cyclization. So we could do, what have I called this previously? I'll use what terminology I've used in my notes. Side, okay. So we can do a head to side. The head, of course, is the nitrogen because we read from nitrogen to carbon, that's the head. Side cyclization. We do that. I apologize for my bond angles, they're awful. So no, we're not binding it to the main chain. We're attaching to the side chain. So the disadvantage here, of course, is if I'm an exopeptide like C terminuses, I've done nothing to stop that. But I have stopped the N terminus exopeptidase as being problematic. And maybe for whatever reason, I want that. Maybe instead of, maybe what I do is I mess this up by stabilizing this by using an unnatural amino acid or something to confuse the exopeptidase on that side. But maybe I really, really want this ring. We can do head to side. We can do side to side. We can, of course, do tail to side, but I'm not going to do that just because exercise for the class. You guys can draw that. Side to side is I couple the two sides together, right? So if I do that, I have some macrocyte. I have no idea how big that peptide block is in between. Could be quite large. It's completely arbitrary. And I have a ring in the middle. Now lots of peptides have multiple lysines and multiple aspartic acids or glutamic acids. So you have even more opportunities for cyclization. So we have lots and lots of different cycles that we can make with a given sequence. These are all peptide cycles. There are cyclic peptides like this in nature. Most of them are in marine bacteria, and I have no idea why. but you see a lot of these things in marine bacteria. Why do they do this? Partially it's for stability. Maybe being in the water, like in the water environment, is a big reason for that. Mostly they're using it for antibiotics. So marine bacteria are using these to make these to kill other marine bacteria because that's what they're interested in doing. In a lot of cases, what a cyclic peptide is and why it exists in nature isn't because of the stability issue. Because unlike us, a cell can just make more peptide, right? The peptide is breaking down, makes more peptide. It's really easy for it to do. For us, when we're making a drug, I have to go back to the factory. I can't just make more peptide on site if I'm using a drug. So it's a little bit tougher. But a big reason for why we see cyclic peptides in nature is because, I don't know, you've seen lots of, I'm going to divert from this for a second. I'm done with this for the day. But I just want to discuss why we might want cyclic peptides and where I think the big future with these is. Start up Chrome. Okay. Let's see if we're a typical binding pocket. Yeah, okay, so perfect. So if we're thinking about drugs, you know, this is perfect. This is a good example. Hopefully this actually brings me to a picture. Not a particularly useful one. So if we have something like this, I don't know why I keep hoping that, oh, good, it's a nice big website. When we think of a protein, we think of it binding a drug to a protein. We're often thinking there's a pocket, there's a hole, there's a gap, there's a groove, there's a thingy, there's like an indent in the protein, and I slide my drug into that indent, and I mess up how the protein functions because the protein either needs that indent for doing things or needs to be able to relax and compress that indent for some other part of the protein to do things. I think I can basically safely say that almost every single drug invented before about 2004, 2003 did this. So, 150 years of drug development targeted indents on proteins. Why? Because it's an indent. Like, I just need to get something that fits, right? Like, I just need to match shape. And electrostatics and all other stuff, but just get something that sticks in there and it messes it up. The problem is we have a lot of what's called, I guess, let's see what I get when I type in undruggable proteins. I want to see a structure of one. So, okay, yeah, here's a good alternative. So what we can have is these kind of undruggable proteins, and the idea here is that there's no real indent, there's no active site, there's no pocket, there's no hole I can stick a drug into. And if I'm making small molecules, I need my small molecule to bind selectively to one protein, not other proteins, because if it binds all proteins, it's not a useful drug, right? So it needs to find a hole. But if there is no hole, there's no hole, and how do I get my small molecule to bind? And I start running around in circles, getting really confused. But a lot of the times proteins work because two proteins come together. It's like these two proteins, the orange one and the gray one, are binding together. That probably does something. The protein then does its thing. So if I want to drug that, and there's no specific hole, what I need to do is I need to design something that interferes with how the two proteins bind. But there's no hole. There's just surfaces. It's like a flat wall. But its two proteins selectively bind at that surface. So the nice thing is cyclic peptides can imitate a protein binding surface. If we design a cyclic peptide properly, it can have all the indents and the slight modulations and undulations that you get on a protein binding surface. We can have all the electrostatics. And so a cyclic protein or cyclic peptide can bind to a protein face that a small molecule can't, because a small molecule needs a hole. A cyclic peptide just kind of slaps onto the face and binds tightly. through a whole bunch of weak interactions instead of a small molecule which binds using a handful of very strong interactions. And so cyclic peptides are, I suspect that by about 2050, 2060, the majority of drugs are going to be cyclic peptides because of new drugs. Because the small molecule stuff will mostly be done. We're figuring out, we occasionally find new proteins, we can design a new drug, it's great. But mostly we're stuck with the things that we're not being able to drug very well right now. And in a lot of those cases, because we're trying to interrupt a protein-protein interaction. And that works because, two protein faces match together. And now we need to mess with that. We need to interfere with that. And the best option we've got is, large flat things, and cyclic peptides are those large flat things. So that's why I think these matter a lot. And I think that's why we'll see marine bacteria produce these, because they're interfering with protein-protein interactions in other bacteria. And we can harness that to create new drugs. So not only does cyclization stabilize our drugs, our peptide drugs, cyclization can actually provide us with the shape that we need to make them into a useful drug. And we're at 9:50, so I'm going to leave it there for today. Try and draw I left the tail to side cyclization thingy in there. Try and draw that. And in the next class, we're going to start by discussing the difficulties with all of this. I'm going to put a couple of review articles in there. I'm also going to put a couple of articles on click chemistry and bioconjugation into the Blackboard. And I think those could be useful to take a read through before we get into some stuff next class. We're going to talk about how we can connect sugars and peptides and peptides and peptides and peptides and proteins and peptides and lipids and lipids and lipids and peptides and nanoparticles and sugars and everything together, and dendrons and all sorts of crazy shit, so that we can start now connecting all these materials together to make more useful functional things. Okay. I'm good. I hope you guys have a really good rest of the week and a somewhat relaxing Wednesday. And I will talk to you all later. Bye.